Okay, good evening. We are now in the fifth presentation on this course. So far, what we have seen is what is an electrochemical cell, how the electrochemical cell is given a notation in the electrochemistry textbooks, and what are the two components, two electrodes, anode and cathode, anodic oxidation, cathodic reduction, and also we have seen an ideally polarized electrode, okay, just like mercury and platinum, which are not taking part in the electrochemical electrode electrolyte reactions but sensing the electrolyte concentration. Now today we are going to see a little bit more on this. We have already seen that there are the IR drop, that is in the electrolyte there will be a small amount of potential drop which will be manifesting as the IR drop. Now the compensation is critical while analyzing fuel cells data for kinetic and transport properties, because this is the loss. We have already seen that in the middle region, in the initial region, the activation polarization, in the middle region is the concentration polarization, and the last region being the mass transfer restrictions. So therefore, we have to compensate for this IR drop, because most of the measurements are in that region. So ohmic drops occur due to IR in the electrolyte and the electrode. The IR electrode should not be neglected. So in IR compensation in both the electrolyte and the electrode shall be discussed in the future lectures. Now we will not take it up, but what is the IR drop we will see. So now mass transport in electrochemical cells is an important area. Now there are three different types of mass transport in electrochemical cells. One is that there are three fundamental modes of mass transport in solution. One is migration, because we are essentially dealing with ionic solutions in electrochemistry. This is the motion of the charged body ions, okay, under the influence of an electrical potential gradient, under the influence of an electrical field. Let us keep that simply that. But it is essentially the potential gradient. The potential changes, automatically the migration also will change. Diffusion, this is the most common of a species under the influence of a chemical potential gradient. Chemical potential, that is electrical potential, this is chemical potential. Diffusion is mainly due to the concentration gradient. Okay, chemical potential gradient. Conversion, this is the hydrodynamic transport, either due to density gradients, natural convection, or due to external means such as stirring, forced conversion. So therefore, convection can be either by stirring or by the density gradients. Diffusion is because of the concentration gradient. Migration is due to the electrical potential gradient. Now, which is important and how to measure all of them in electrochemical reaction? The governing equation for mass transport in the Nernst-Planck equation for one dimension, okay, one direction. We are only talking about the migration to the electrode. The flux J of x in the x direction is equal to minus d. D is the diffusion quotient, the units of centimeter square per second. Delta Cx by dx. Delta Cx by dx is the concentration gradient. Concentration gradient is the diffusion, chemical potential gradient is the diffusion phenomenon. Minus Z, the charge on the thing, F Faraday, RT into D, diffusion quotient, into C, the concentration, into d phi by dx. This is the potential gradient. Potential gradient is due to migration. Plus C into Vx. Vx is the velocity with which the element of a solution moves in the x dimension. So this is the governing equation. Now in this we will choose the conditions in such a way, one of them will be predominant. Faraday's law is the current produced proportional to the number of moles of the reactant in solution. M, the is number of moles is molecular weight into current into time divided by N, number of electrons, F, the Faraday. Conveniently written as the I by N of A is given by M by M, capital M into T into A, where N is the number of moles. Capital N is number of moles, T time, A amperes current is the flux. So don't confuse yourself with a capital N and small n. Small n denotes the number of electrons transferred. Capital N denotes the number of moles reacted or electrolyzed. So therefore, we want to make one of this, for example, these three transport phenomena: migration, diffusion, and convection, in which we want to make one of them. The larger the current, the faster the rate of consumption. That is a Faraday's law. The reactants arrive at the electrode via transport from the bulk. So now, for a maximum transport of flux is equal to reaction flux into reaction is mass transport limited. So J is simply equal to I by N of A. This is the equation we have already done. Okay, J is equal to N of A by I by N of A. The reactant concentration at the electrode is equal to 0 to start with. All reactants immediately consumed. When the rate of the reaction and the electrochemical reaction is fast, the reaction cannot proceed at a rate faster than the mass transport limited rate. Under those conditions, the reaction rate can be only controlled by the mass transport, electrochemical reaction. Okay. So assume that no convective mass transport. Okay. Convective mass transport is, already we know, is to the hydrodynamic density gradient or the stirring forced convection. So therefore, no convective mass transport, negligible transport due to migration also, then only the convection current also is nearly zero, migration current also is nearly equal to zero, then the current will be diffusion current. This is what is the most common current that we measure. Flux at the electrode may be written as J is equal to minus D into dC by dx. In this equation, only the first term is prominent. The two other terms are due to the migration and the convection. So D is the diffusion coefficient of the reactant and dC by dx is the concentration gradient. So if I were to look at the thin layer that lies intermediate bounds the electrodes and the bulk. So if the bulk concentration is C is equal to Z0, then the very near to the electrode up to a distance from the electrode is at the distance it is equal to 0. So if diffusion is controlled, therefore the species that is arriving at the electrode is immediately discharged or electrolyzed. So therefore the concentration gradient at the electrode is 0. The concentration gradient at the bulk is C0. Therefore in the intermediate distance from the electrode to the bulk of the solution, it is linearly varying like this. So D is the thickness. So a thin layer of electrolyte, thickness delta, okay, thin layer of electrolyte in contact with the electrode surface, ion transfer controlled solely by diffusion. So under these conditions, the electrochemical reaction is controlled by diffusion. So therefore, we will be dealing with these diffusion controlled reactions. This is what you are using in your polarography and all other things, because you are only worried about the diffusion current. Concentration species maintained constant outside the layer by convective transfer. Okay, here in this region, the concentration is equal to bulk concentration, because whatever concentration changes take place, that is compensated by convection current, that is either by the density gradients or forced conversion. So, as we have seen, the concentration gradient in the Nernst diffusion layer, Nernst diffusion layer is linearly varying. So therefore we are assuming that, okay, then J will be equal to D into by D by delta. Delta is the thickness, okay, into concentration at the bulk minus the concentration at x is equal to 0. At this, the concentration here and this. So therefore the concentration gradient is this. So D is the delta is the thickness of the Nernst diffusion layer. C star is the bulk concentration of the reactant. C is the concentration at the electrode surface. X is equal to 0. So the mass transfer quotient D, okay, difficult to obtain precisely the values of delta, the Nernst diffusion layer. Therefore, D is grouped along with the capital D, the diffusion quotient, to yield a new constant Km. Km will be equal to D by delta, where Km is called the mass transfer coefficient in the units of centimeter per second. I hope you are able to see this is a one-dimensional transport, centimeter per second. So now J, the flux is I by NFA. We have already seen that. Combining this with all the equations, we get I by NFA will be equal to Km. Km is simply the diffusion quotient by the thickness of the Nernst diffusion layer into the bulk concentration minus C at x is equal to 0. Current dependence on the reactant concentration. So as reaction proceeds faster, at some point all the reactants that reaches the electrode is consumed immediately. At this point, C at x is equal to 0 is 0, and the current levels of can be written as I, the limiting current, is given by NFA into Km into C star. L limiting current is called the limiting current. This is what we are measuring in many of the electrochemical measurements. So relationship between surface and bulk concentration we have already seen is C0 at x is equal to 0. C, the concentration at x is equal to 0, and the bulk concentration. This is given by 1 minus I by IL, the limiting current. Substituting for the C star from this equation, C is equal to I limiting current minus I by NFA Km. Both equations reiterate that surface concentration is equal to 0 at the limiting current. The limiting current is, that means all the species that is arriving at the electrode surface is consumed immediately. Significance of the limiting current. Okay, this is very important for us because in many measurements we are measuring this maximum current obtainable for a given set of conditions. Very important in fuel cell and other operations. Generally, higher limiting current implies lower mass transport losses, higher efficiency. Significant research efforts devoted to enhancing the limiting current in PEM systems. PEM means polymer electrolyte membrane fuel cells. So what we are trying to do is we are always trying to optimize the limiting current. So limiting current is optimized means the other mass losses are reduced. So now we will see a few, very few, okay, few electrochemical experiments, common experiments. Now, one of the measurements that we do is always we are doing it in a potential stat. Whether you do a cyclic voltammetry, whether you do amperometry, chronoamperometry, whatever you are doing, this is given by a potential stat. Potentiostat is a potentiometer, but only thing is it is not a potentiometer in the sense that you are having only two electrodes. Here we have three electrodes. We will see what is the significance of this. So therefore, what it means is the two electrodes are the working electrode and the counter electrode. Okay. So now the potential is monitored by a device. That is what is shown here, that it is put on earth potential. So it will adjust itself, the resistor or the point of contact will adjust itself so that the potential applied on the electrode is a constant parameter irrespective of the potential on the counter electrode. This is why it is called the three electrode system. The third electrode is called the reference electrode, which is also there in the circuit of the working electrode. Across the reference electrode and the working electrode, you are measuring the potential and current. That is what we are doing. Okay. If you are measuring working electrode and the counter electrode, it is a potentiometer. If you are measuring with respect to a reference electrode and the working electrode, then it is the potential impressed on the electrode is a constant parameter. That is what is a device, or we will have time to talk about how to construct a potentiostat. Here I got shown a picture, but how to construct it we will show you later on. So therefore, that is very reference electrode is normally standard hydrogen electrode, SHE. An ideal reference electrode is one that maintains a constant potential irrespective of the amount of current, if any, that is passed through it. Okay. So an ideal reference electrode is one that maintains a constant potential irrespective of the amount of the current that is passed through it. Standard hydrogen electrode is also called a normal hydrogen electrode, simplest reference electrode. This electrode potential by definition is equal to zero. Now I will show you a construction of a potential. The electrode process in a standard hydrogen electrode is H plus in a 1 molar so aqueous solution. A activity is 1. We have to understand the activity. We will see later on. So if I were to add an electron, then hydrogen will be evolved. If this is the equilibrium reaction, if I subtract an electron, then hydrogen will be becoming H plus ions. Consists of a platinum electrode immersed in a solution with a hydrogen ion concentration of 1. A is 1. Activity is 1. The platinum electrode is made of a small square platinum foil, which is hydrogen gas at a pressure of 1 atmosphere is bubbled around the electrode. This is the hydrogen electrode. So you can see this is the platinum disc which we were talking about. Platinum disc which is dipped in the 1 molar HCl solution or H plus solution, or the activity is 1, not molar. Okay. It is very difficult to obtain unit activity in practice. That is why we are talking about molar. Okay, which is easily maintainable. Hydrogen gas is passed through this at 1 atmosphere pressure. So this is the standard hydrogen electrode construction. You simply take a tube, a glass tube, fuse a platinum wire and a platinum foil, and keep the bottom open, and the hydrogen gas is passed through the side tube that you have. This is the simplest design one can do. But it is not, this standard hydrogen electrode is not widely used because it is very difficult to construct. Construction is not difficult, but you have to maintain hydrogen pressure at 1 atmosphere. You have to keep the concentration of the electrolyte 1 molar, or activity is 1. So therefore the hydrogen source has to be at atmosphere pressure. So this is why it is so the standard hydrogen electrode not widely used, difficult to obtain solution of 1 molar. 1 molar is not correct. 1 activity is 1. Saturated calomel electrode is very popular as a reference electrode. It is electrode is mercury coated with calomel. Well, calomel means Hg2Cl2, single electron transfer. Electrolyte is a solution of potassium chloride and saturated calomel. So Hg2Cl2 solid, two electrons are exchanged, then two mercury will be there. It's a single electron transfer, but there are two mercury atoms. That is why two electrons are there, and two Cl minus. This is the equilibrium reaction that takes place in the electrochemical calomel electrode. We will have opportunities to talk about all those electrochemical reactions little later. Okay, we will see them in a later. So this is the how the calomel electrode is constructed. Saturated calomel electrode, SCE. Okay, this is a mercury. Here we are having a coating of mercurous chloride, Hg2Cl2. The saturated KCl solution is put there, and KCl crystals are at the bottom, so that if anything happens, it will be always a saturated solution. So therefore, the contact is through the mercury. The wire is taken and connected to the whatever instrument you want to deal with. Now the linear sweep voltammetry, hydrogen gas passes through counter reference electrode, nitrogen passes through the cathode. Working electrode, fuel cell, in the case of fuel cell, cathode subjected to potential sweep from an initial to a final value, typically 1 to 800 millivolts. Sweep done using a potentiostat. We will see later on what is the potentiostat and all those things. We have already shown you a potentiostat, but why potentiostat and why potentiostat construction is important, we will see, take it up later. Sweep is done using a potentiostat. Fixed sweep rate. Sweep rate has to be constant. We'll see later on. These are the very important variables in electrochemistry. The sweep rate, because we don't have any other variable. I already told you current and voltage alone is the thing. So therefore, if you want to study the kinetics of the reaction and the thing, you have to only manipulate how you are applying the potential and measuring the current. So sweep rate is one of them. And then what you are measuring is linear sweep voltammetry. You are measuring the Faraday current is monitored. You are, as we have said, voltage versus current is measured. So for example, 0 to 800 volts, the current is measured as a function of time. So the scanning of the voltage is 4 millivolts per second. This is a common thing, but it can be different. It can be variable value. Hydrogen only species present crosses over from anode to the cathode to the membrane, gets oxidized at the cathode at positive potentials above zero. So the data obtained in the okay, we will not deal this here. We will take it up later when we are doing the PEM fuel cell. So when the potential is zero, no net Faraday current. When the potential exceeds zero, Faraday oxidation, hydrogen gets oxidized to H++ electron. As potential moves to more positive values, over potential electrochemical driving for oxidation increases. When we go on increasing the potential, we are more or less applying the over potential. Therefore, the electrochemical reaction, oxidation reaction increases. Reaction proceeds faster until it hits the mass transport limitation. Since hydrogen oxidation kinetics are fast, this limit is quickly obtained in the case of hydrogen. But in the case of other species, for example, cadmium ion getting discharged and all those things, it will take a certain potential. So above a certain E, reaction becomes mass transport limited. We have already seen this. So therefore, that is what is called the limiting current. In the case of limiting current behavior, the current can be converted into a reactant flux using the Faraday's law. We have already shown this. The flux, in the case of hydrogen, if hydrogen is the depolarizer, hydrogen is the reactant, the moles per square centimeter per second is given by the current density divided by NF, where I is equal to 1 milliampere per square centimeter from voltammogram. Okay, Additional details, the experiment is typically done at a low sweep rate. We have already said 1 to 4 millivolts per second or even lower than this, 0.1 millivolt also we will do. But we will take it up later on when what is the effect of the sweep rate, why we cannot take high sweep rates and other things. We will do when we do cyclic voltammetry and also other voltammetry measurements, we will talk about it. This is to ensure that NAND's diffusion layer has the time required to grow out from the electrode. Okay, why small sweep rate is used? This is the true for even for cyclic voltammetry, but we can do in cyclic voltammetry higher sweep rates. This results in true limiting current behavior. In practice, it is better to start the sweep at higher potential to avoid effects of hydrogen evolution. The utility of linear sweep voltammetry will be further discussed in the future lectures. Cyclic voltammetry. This is one of the experiments that you are commonly using that. Therefore, we will see that a potential sweep experiment similar to linear sweep voltammetry. Additional reverse sweep is incorporated. Linear sweep voltammetry is only 0 to 800. Okay, just a minute. Hello. Uh, uh. ನೀವು ಒಂದು ಇಮೇಲ್ ಒಂದು ಮೇಲ್ ಅನುಪ எனக்கு ಸರಿ ಸರಿ msmoni ಡಾಟ್ ಓಕೆ ಓಕೆ சரி நாளைக்கு அனுப்பிச்சுடுறேன் இருக்குப்பா. Sorry for the interruption. Additional reverse sweep is incorporated in cyclic voltammetry. That is, your potential is 0 to 800. From 800 to 0 also you are doing. Start from E is equal to E1, sweep up to E is equal to E2, sweep down back to E is equal from E2 to E1. This is what is called the cyclic voltammetry. Done using a potentiostat. We have already told you that all these measurements have to be done using a potentiostat. We will see later on why it is so. Fixed sweep rate. I have already talked about the sweep rate. It has to be smaller, but it can be higher in the cyclic voltammetry, but not in linear sweep voltammetry. We will come to it, all of those things. What you are monitoring is the Faraday current. Faraday current means the current due to the electrochemical reaction. So this is a typical voltammogram in an electrochemical cell, cyclic voltammogram. So the potential is from 0 to E2, E2 to E1. That is what you are doing in this. So the redox reaction is oxidation plus N electron giving rise to reduction. So the output will be looking like this. This is the forward scan. This is the backward scan. If it is a reversible reaction, then the current, okay, the current, the E forward, E backward, or E oxidation, E reduction, all those things have to be a certain value. We will come to it, all those values. Like also okay, we will not take it up now. It has to the shift in the peak positions must be 59 millivolts if it is a reversible system or one electron system. So we will see later all those things. So the typical CV at a fuel cell cathode is 2H plus 2 electron giving rise to H2. Okay, I told you the linear cyclic voltammetry is 0 volt to a 0.8 volt, 0.8 volt to again to 0 volt. So therefore you can see that it is a more positive value oxidation, negative value reduction. The reduction as E becomes more negative. When the E becomes more positive, oxidation takes place. So therefore the output, the current that we are measuring is the oxidation current, is the reduction current. So response of the fuel cell resultant current behavior on the forward sweep, same as discussed for linear sweep voltammetry. Hydrogen get oxidized to give rise to H plus electrons. Behavior on the reverse sweep, the opposite of the redox phenomenon occurs, that is H plus gets reduced, gaining electrons in the process to give rise to H2. Peak symmetry indication of the reaction reversibility. All those things, there are certain criteria. Each of these criterion can be used to study the nature of the electrochemical reaction that is taking place, whether it is a single electron reaction, it is a reversible, completely reversible, or quasi reversible. We will see later on what is quasi reversible and reversible. Reversible we understand. What is quasi reversible? Either reversible or irreversible only possible. What is quasi reversible? This is also a question that we have to ask. This is a very common thing in electrochemistry, quasi-reversible, so we have to look at that. Additional details are sweep rate employed are typically higher than those of the linear source. We already talked about it. Linear sweep voltammetry will be 1 to 4 millivolts per second, whereas in the cyclic voltammetry and other things, it will be even 100 millivolts per second. Okay, but commonly 5, 10, 20, 30 millivolts per second is used. Peak height scales as V is equal to V to the power of half. We will come to it, all those things. In the electrochemical equations, you will have some power. Okay, we will see what is the power and how this power is. For example, you take polarography, T to the power of 1 by 6, like that, it will be there. You will see all of T to the power of. Thus, larger V value, better defined peaks. Need to ensure sweep rate is not too high. System tends to become quasi-reversible or irreversible. If the sweep rate is very high, it becomes quasi-reversible or irreversible. Applications of all these things, we have only taken two measurements. Once you have a potential stat, you can make about 200 different types of measurements. We will see all of them later. Voltammetry, amperometry, okay, pulse polarography, pulse measurements, all kinds of measurements can be done. We'll see later all of them. So the applications are studying the reversibility of the reactions and redox behavior of the compounds, used to obtain quantitative information about the extent of reaction occurring on an electrode surface. In fuel cells, used to determine electrochemically active surface area of the catalyst. This is one of the important parameters of the fuel cells. We will see that the active surface area is not equal to the geometric surface area. Okay, so we have to determine this. We will do this. So we will stop at this point and answer some questions if you have.